Hello and welcome everybody to Advent of Code 2023, day 20. We're in the home stretch now, only a few days to go. Definitely some trickier problems have been coming up this year, I think, but today wasn't a super difficult problem. I think most of the difficulty was in reading and understanding what was actually being asked of you. After that, if you could correctly simulate what the rules were, the answer for the first part was pretty simple if you got the simulation right. And then this is another classic case where he wants you to be able to do something correctly in the first part. And then assuming you're able to do that, you can use that as a tool to solve the second part. And of course, the second part also involves something that's a number far too large to simulate. So you can't brute force it. So you need to come up with some other means of solving it. In this case, it's very similar to a previous puzzle this year where we have a looping pattern and we can use the exact same thing, find the points where the pattern loops and do a lowest common multiple on that, and that will work. So you can simulate a much smaller range of values, find the values where the loop happens, get the lowest common multiple of those four numbers, and that gives you your answer. So that's pretty fun. I'm kind of pressed for time today, so I'm going to try to rattle through this as quickly as I can. My code is very verbose. I'm not going to go into every minutiae of the details, but yeah, let's go through it anyway and talk about it and see how we get on. So day 20, pulse propagation. So they fixed the machine that makes the sand, but now the machines are way off out in the desert and they don't communicate with them directly. They use this like relay system of nodes to... Oh, I don't know if that came across on the microphone, but the cat just scared the life out of me. Anyway, thanks, cat. The relay system sends these like pulses, so they're like high-low, like 1-0 pulses almost, and that is how... And so that propagates through this network, and then the nodes on the network command the machines to do the stuff they need to do to make the sand, so on and so forth. So I'm going to kind of skip through a lot of this. It's quite detailed. There's basically these different types of nodes that you're going to encounter. So there's 4 total types they tell us about. One of them you don't really need to simulate, and then the other 3 you sort of need to simulate. Really, you only need to simulate 2 of them, but for the way I wrote my code, I simulated another one of them as well. So the 2 that they tell you about that you need to simulate really are the flip-flop node and the conjunction mode. So they say here that a flip-flop mode has 2 states. It's got an on and an off state. And they always start in the off state. When they receive a high pulse, they do nothing. When they receive a low pulse, they flip their state and they ping a message off to what they're connected to with that new state that they flip to. The conjunction modules work slightly differently. So they keep a memory of all the states that talk to them, what the values are. When those values all go high at the same time, then it sends out a low pulse. And otherwise, when they receive something, they'll send out a high pulse. So then there's another module called the broadcast module. So this is the very start. And basically all the broadcast module does is it sends out a low pulse to anything it's connected to. There's also then, this is the one you don't really need to simulate at all, which is the button module. So when you press the button module, it sends 1 low pulse to the broadcast module. So then the broadcast module will forward that on to all the modules it's connected to. So the button module, you don't really need to simulate it, but imagine the start of each cycle of the simulation is the button being pressed. So hence why they've called it the button module here. So they give you this is our input, and this tells you the map of the whole thing. So we have our broadcast module here, and we're told it connects to modules A, B, and C. Then we've got all the other modules down here. We're told the way that they're labeled is they have a prefix to the module key, and that tells us what type it is. And then they're just A, B, C, whatever, and they're the individual modules themselves. And then it shows what they're connected to, and that's it. So what we're told is basically if you trigger this broadcast module, so you press the button once, we're told that it'll go through some pattern. And we're told the way this works is each module sends its pulse out to each of its destinations. So they all get sent out. And then each destination in order receives those pulses and then does something with them. But this is where I got very confused at the start. This isn't a recursive tree thing. So you're not going all the way down following the pulses through, because no sub-module, no destination module can respond to a pulse until all of the pulses have been sent from the parent module. So you're not doing a recursive thing where you're like trying to get down to the far end of the tree like a depth first search. It's a breadth first thing, basically. So that took me a while to get my head around, but once I got that, then this became a lot easier. So yeah, basically it says that, so this is, if you press the button once, you end up with this whole pattern being generated, and this pattern has a certain number of low and high pulses to it. And yeah, so it says each time you press the button, you'll get the same pattern repeats, and the state comes back to 0 again when this pattern is repeated once. So the state comes back to its initial default state. It gives you a different example down here, which is slightly different, and what it tells you is basically it's an alternating state thing. So when you press the button once, you'll end up in some position. If you press the button again, it ends up with a different sort of state position, which you can see here listed out by the list that happen. So anyway, get this idea. You press a button, you follow the states through. It'll give you some amount of high states and low states being generated throughout the whole thing, or pulses being sent. So what we're told to do is, we're told in the example text that if you do this 1,000 times, if you press the button 1,000 times and simulate your states 1,000 times, you'll get a certain number of high pulses and a certain number of low pulses in total that have been generated. So based on that, you want to take those high pulses and low pulses counts, multiply them together to get an answer. And this is a validation thing, that if you get the right answer, it means you've been able to correctly simulate the states, how they move through them. And that's basically all it's doing for the first part. So do it 1,000 times, see what your answer is. That is if you were to simulate it. So I went down the simulation route for the first part. So I wanted to be able to simulate one time and then just do it 1,000 times and then see what your answer is. So let's have a look at the code and see. So first thing you'll see here are these horrific looking lambdas. I'm not going to go through them in massive detail, but effectively they handle each operation, each operation that happens with each type of node. So for the broadcaster node, basically what it does is it just takes whatever the pulse that you give it and it just redistributes that pulse out to all the destination nodes. So we do that here. The main part is in my model, each node has a queue, and that's a queue of the points of the pulses it's receiving. So you're supposed to basically, you're supposed to process the pulses in order that they've been received. So if you use a queue, you can push onto the end of the queue and pop off the front of the queue every time you want to process a node. And effectively, you'll keep processing until your queue has reached 0 for every node. And then you know you're done because there's nothing else that's going to happen for the button press. Similarly, they all basically do that. They all go through the destination nodes and they send out what the pulses should be. The only two things we have for the flip-flop node, we have the logic for the flip-flopping case, and then for the cumulative node, we again have the logic for the combination node, you have the logic for that in there. So down here, so those are the lambdas that are set up just to handle my operations. But the first thing the program does really is it goes through the file and picks and basically builds our map. So I'm using a hash thing as a map, as I love to do. I also build this reverse map, which is for a very specific thing, which I'll just talk about in a second. So yeah, this goes through it. Nothing doing anything crazy complicated, just figuring out what the pattern is with the source and destination nodes, and sets up the state and an empty queue for each node. The state for the flip-flops, I just give it like its own key and then say that it's false because that's how we initialize them. And then when we come down here, this is what I used the reverse map for. So the reverse map is a little bit more complicated, but basically this is, well, what connects to that node, because we're told in the text that the what is it called, the conjunction node, it basically is initialized with everything that connects to it, and it's initialized with them all being false. So from the start, you need to know everything that's connected to one of those nodes. So from that, we use this reverse node, which is just a backwards mapping that's been recorded as we went through the original setup. And we use that to set up this reverse node state so that it has each of the things that connect to it and it initializes them all to false. Okay, so we've done that. Now we're down to the actual simulation code that does this. I have a while loop here set up, which will just keep executing until we have our break condition met. And in my data structure, my break condition is basically the queues that are maintained on each node that contain the pulses they've received. When we've exhausted all of those queues, we hit our break condition and we stop, because we've basically, you hit the button, it sent out this propagation that went out through the whole network, created some loops and stuff, but once all those queues have been exhausted, they have nothing else to do, then they'll stop and that'll be it. Yeah, and that's basically it. So the way you do this is, I just loop through the entire map. So I loop through every node in the map in the order that they're listed out in, and effectively I check the queue, I pop shift off from the top of the queue, and that gives me what that pulse is, and this will maintain the order. So if a new one comes in, it'll go to the end. I shift it off from the top, and I just run the operation based on the type with that pulse, and that's it. I count, then in return I count all of the pulses that are being sent out. So that's another thing that the lambdas do up here. So they stick a new pulse into the destination queue, and they also just record a list of pulses, which I'm then just appending to each time. And that then eventually, when this finishes, gives me the total list of all of the pulses that were sent out for the whole thing. Okay, so that was a little bit messy, but let's not worry too much about it. If you go through this code line by line, you can kind of convince yourself that it does work. But anyway, I can show you. So if we run our simulation on the sample, yeah, it's not terribly fast, but that is the correct answer. We run it on the second sample that he gave us. Again, that is the correct answer. And then if I run it on my input, it's not super fast. It should run in about a second or so, I think. Yeah, a second and a half. And that is the correct answer. So, moving swiftly along, let's have a look at part 2. So for part 2, it's again one of these suspiciously small part 2s where they give you very little information and just say, do thing, and they don't even give you a sample that you can test on. So that's kind of fun. What they say is that one of the nodes in your whole graph is the one that sends the sand tumbling down to the island below. So you need to figure out when that one will be activated. And that should be, in a case you think about it, it's like, oh, well, I'll just simulate that. But that's how many iterations of the simulation it would take for you to get there. Very big number. You're not going to do that. So first thing your head should jump to is, okay, is there a pattern I can use to determine when that will happen? And there is. So basically, if we look at our input file, so if we go to, so we search the file, we look for ORX, we see there's only one ORX, and it gets pushed to by this conjunctive DF. Okay, so let's have a look at DF and see what that is. So DF is, so if we just search for DF, we've got 4 things that all push to DF, right? So this should seem kind of reasonable that, so we know, because of the way our rules work, the conjunctive will send out a low pulse if all of those are high. So what we have to do is we don't have to simulate to get all the way to where ORX is low, which would be DF being low. All we have to determine is when do each of these nodes that link to it, when do each of those go high? Once we know when they all go high based on the things, we know because of the looping nature of the pattern that we'll get the lowest common multiple of those 4 count numbers, and that will give us our answer. So we'll have a look at the code for that. So it's the exact same, all the code's pretty much identical, except when we go down to our loop, instead of having a break condition, or instead of just looping 1,000 times and getting an answer, I'm looping some arbitrarily high number of times. Now this is suspiciously close to the values that you'll get out for down here, but that's on purpose. I initially ran this, I think, for 5,000 iterations, and I found what was the answer. Complete guess, but it gave me answers, so I think that's all you need to worry about. And so yeah, down here we just check these values. So this is each of my inputs into that conjunctive one. Check when they go high. The first time when they go high, stick them into this dictionary, and then get the lowest common multiple of those numbers, and that gives us our answer. I'm not going to run this because it takes a few seconds to run. Well, I'll see if I can show you if it finishes while I'm still talking, then that'll be good. But yeah, so you see these numbers are going to rattle up, so they'll get up to 4,060, and then that'll spit out the answer. So it takes a couple of minutes. You'll notice that as this goes, the numbers actually start slowing down, and that is because of this tally operation I'm doing in here. I'm doing that with every iteration of the loop, and that tally operation is relatively expensive, but it becomes more expensive the more pulses you get, and obviously the pulses continue to increase after every iteration of this. So yeah, it'll take a few seconds to complete. So I'll leave that running. Maybe I'll say goodbye to all you folks, and then this will spit out the correct answer. So I think I just assumed that this was going to be a looping pattern problem. Often with these things, you'll sort of discover that it's a looping pattern by looking at the outputs loads of times and realizing. I sort of just assumed that, and kind of assumed that, well, it'd be a relatively small number of iterations would give it to me. And it did work out. That assumption could have been completely wrong, and then this problem would have been way more challenging to get to the solution. But it just so happened to work out pretty nicely. So that's a win. It doesn't always work out as nicely as that. But that said, my code is still relatively slow. You're seeing like this operation is taking quite a while to get to an answer. It's faster than just an all-out brute force, obviously, which for my code, God knows how long that would actually take to complete. But yeah, I think that's really about it for today. I hope this helped. I'm sorry I rattled through this all so quick. I didn't really go into all the details, but the code isn't the prettiest. It's a little bit verbose. And as I said, I'm a little bit pressed for time today, so I couldn't talk through every single line. But yeah, I hope this helps someone. Any questions, even in the comments, I can try and clarify any points that I may have just glossed over. This is just about to finish in a few seconds. You can see it's slowing down as that tally operation becomes more expensive to execute. But we're almost there now. Let's go. Come on, baby, you can do it. 3, 2, 1, boo! There's the answer. So that took over just over 2 minutes to do. So yeah, not crazy. You can sit and watch it, but it's also not super fast either. So that is it for today. Hope you guys had fun, and I will see you all tomorrow for day 21. See you now.